Hi, welcome to Chapter 4. Hope you had a good week. So hopefully in this chapter we'll be able to look into, kind of talk to about what a queue is, how to design it, how to use it, some of the operations involved, how we're going to implement it using a linked list structure versus an array. Understanding a little bit about the operation in queue via the ADT, it uses C language. I'm not going to lecture on the C, but that stuff's in the class if you're looking for the actual code. And then kind of talk about a couple examples where queues are being used, categorizing data, and maybe in queue simulation. So just give you a rough idea. So, of course, what is a queue? Well, basically, queue is just a line of people. You've been in them forever. You're probably going to do one today or tomorrow, and turn your paycheck into to the bank. You stand in line. Server takes your check, makes your deposit, gives you cash back, and you leave. You go in one way, you come out. So we all understand that. Well, a computer does the same thing. You enter the front and you leave through the rear. Or in this case, they're saying, hey, you're going to enter and get in the back of the line. I like to cut in front. So, but you can enter in the rear, go out the front, and somewhere at the front, somebody's going to serve, whatever needs you have. So whether it's a bank transaction, writing a record to a database, several different things. So we kind of understand the concept of a queue. Now, what we're going to hope to do is look at some of the four basic operations. Kind of give you some graphs and stuff and show you how it works. So basically the four are: in queuing is inserting elements into a queue. DQ is removing things from a queue. And then there's two, queue front and queue rear, where I'm going to get data from either the front or the rear, but I'm going to leave the queue intact. So I'm just gathering data at what's the first or the last thing in the queue, and I don't care. Now, I'm not going to change it, not going to delete anything, because that DQ deletes an element from the queue. So the front and the rear are basically the same, just which end am I looking at there. So just give you a graphical image as to what it may look like when I'm in queuing and putting something in. When I'm, whether it's one, into a blank queue or one with one already in it. So, got an empty queue, have green, want to be put in place. When I get down, I'll have one element of green in queue. Now, if I want to add blue, I start with my queue with green in it, add blue. Now I got them both. But you notice what happened here is what? Green stayed to the front, blue is now the end. So, this, when I'm going to take things off, when I'm a DQ, the only way I can get things out is from the front of the queue. So in this case, DQ, green's the one that gets removed, leaving blue in its state. And then when I encode again, blue goes to the end. So now, red goes to the end, sorry. So conceptually, I think we understand, standing in a line and first come, first serve. First in, first out. A few more examples with a little bit more, but this one's showing you when I do a queue front, what am I just returning? I am returning just the first element. Now the queue itself stays intact. Same thing with queue rear. My queue stays intact, but I just give you the answer for the last element in there, in the queue. Now, in a linked list, if you want to see the array implementation of this, there's an appendix in the back of the book that goes through how to do this with array. But in a linked list operation, we're going to look at, there's basically two things that we need to worry about: the head node and the data node. So the head node, remember in our stack, what you have? You had data and a pointer. Well, the head node has a structure that has a front of the pointer and a rear pointer and then a count. So that structure of that head node is a little bit different, but all it's doing is giving you pointers both the front and the back of the queue and how many elements are in the queue. And then the node itself, that's going to get stored in there, is going to be the data itself, and then a link to the next item that's going to be pointing to the back of the rear and to the back of the queue. Now, some of the algorithms we're going to look at is, here's our concept here. Here's our head node. Oops, where'd my pointer go? Here's my head node. I got my front pointer, rear pointer, and the number of elements in my queue. So we can kind of got plum, kiwi, grape, and fig in a line. When I look at it computer-wise, I've got a pointer to the front, pointer to the rear, and counting the number in. So you can kind of tell. So we can kind of see where some of these functions could work. So as far as the data structure we're going to look at, as you can see, the head structure basically is what? Front, a count, and a rear pointer. So you got 2 pointers and the count. And then our node structure is the data that's going to get stored and a link to the next one. So as you can tell, not much different from the stack, except we got rid of 1 pointer. So here's just an idea of just some basic functions. I'm not going to go through in detail, but you can pretty much go through the different functions and see what happens as far as the way the pointers are moved when you're doing the 4 different functions. Now, let's look at the algorithms that we'll use a lot in creating queue. So here you've got the create queue. Now, what do you have to do? You've got to create and initialize the queue structure. What do I have to do? I've got to allocate the memory. I set the 2 pointers to null, and then set the count to 0, and then just return, the pointer to where that node has been created. So relatively straightforward. We saw the same thing when we did a stack. Here's just a rough idea. This is what, when you look at insertions, there's 2 different things with insert you got to take into case. There's 2 cases, I should say. One if the queue is empty, and one if there's data in the queue. Conceptually, they're similar, but just knowing that you're initializing pointers a little bit differently. Because in the first one, when there's nothing in there, here's the new data I want to insert. It's got the new pointer pointing the new data. Now, when I do the insert, what do I have to do? I've got to set my front and rear pointer to the same location, the same link, and and then nothing else changes. So, but if I've got data already in the queue, in this case I got plum and I want to add kiwi, and my count's 1, so what do I have to do? I have to change the rear pointer to the new. I change the null pointer from plum pointing to kiwi, so that I've got a continual loop. And then what? Also increase the count. Now, in some cases, whether you want to free up the pointer to kiwi, a lot of that depends on your application. So depends on what you're trying to do. So let's take a quick look at the algorithm for inserting data in the queue. Again, what's my precondition? I've got to make sure the metadata structure exists. So it's already been created. I've got a count, 2 pointers set up, and an address to that. And then what data am I going to insert? So, of course, what am I going to return? I'm going to return if it's true, if it's successful, false, if an overflow. An overflow says what? There's no memory available to be able to allocate that new space, that new node. So 1, I check if the null is, if the queue is full. If it's not, go ahead and allocate space for the new node. Move the data into the new node, set the pointer, to the next node. So I got that new node is now going to be the next pointer. And then now here's my case where I've got 2 different, is the queue empty? Then I'm just going to set the queue front to the address of the new data. If it's old, now I'm going to just set the pointer of the rear node to the address of the new node. So when you look at here, it's like, here's my address. So what I got to do? I set link here take this from null, point it to Kiwi, and then change the rear node and point it to Kiwi. So both of these, basically it moved the same place, and we don't free up that new pointer. So it's just relatively, and of course, don't forget to increment the count. So it's a fairly straightforward operation as far as, like I said, the only two tricks here is one, making sure there's memory, and two, verifying is the queue empty or not. Now, if I wanted to delete, now remember, deletes always come from the front of the queue. So in this case, I've got plum. When I got rid of it, everything's emptied. So what did it do? In this case, it nulled out both the front and the rear and reduced the count. Just about what you expect to do. If it starts out with plum and kiwi in, and I want to delete from the queue. Now, granted, I'm deleting from the front of the queue. So I go to the front pointer. It points me to the data I'm going to get removed. So what do I got to do? I've got to change now my new front pointer to Kiwi, the next element. So I'm going to match the link that's in plum now, move that to Kiwi, and then I can free up that data. So I think we can see graphically what it looks like. Now let's see what the algorithm looks like. So here's our queue empty. If it's false, get out. Now I've got to say here, I got to start getting ready to delete the data. So what I got to do, I got to move data to the item. I don't like the size of this one, but oh well. If only one node in the queue, I just make sure the front and the rear are set to null. And if it's not, then I just set the queue front to the queue front next and decrement the count. So not too complicated. Now, front queue and rear queue, front of the queue, rear of the queue, are basically the same thing. Remember, I'm just getting data from the front or the rear without changing the contents of the queue. And then, of course, data out is where I'm going to store the data. So pointer to the queue, where I'm going to store the data. Check if the queue is empty. If it is, I can't give you a front. Otherwise, I'm just going to copy the data front to data out, and we're done. The same thing would be for the rear queue, but you just what? I'm checking which pointer am I looking at. Now, the question is, queue empty. There's plenty of ways you can do queue empty, but probably the easiest one is just check the count. If the count is equal to 0, it's empty. If not, it's got data in it. Now, the full queue depends on which language, may be difficult to code. In C, it's difficult. Some other languages not. It basically says if there's no memory in the machine, yep, I'm full. I can't do anything else. If there's still memory left that I can allocate, then I'm going to return, false. It's not full, and we're good. So, but based on the language that you're programming in, this one may be a hard one to do, but conceptually, I think you can understand it. The count, well, since we have a count item in the head node, guess what? I'm just going to return that count, and I don't have to do any sequencing up and down the array. Like if I had to do an array to do the count, you would have to start at the beginning, go all the way to the end, counting every single item just to double check the size of your array. Now, destroying the queue says I'm just going to take all the elements out of the queue. One I have to input is I got a data for the queue, and when I'm done, I got to have all the data gone. Now, basically what I'm doing, I am just looping through the queue and deleting the front node. So I'm just taking things off the front of the queue until we're all done, and each one just gets rid of, because remember the delete, it freed up the memory of what it got rid of, and then once I've gone through the whole list, the only thing I can do is delete the head structure. Now, queuing theory, oops, I think I left a slide in here. Let's go back to this one. Here we go. queuing theory is just a theory of applied maths. Actually, I enjoyed in college taking a queuing theory class, but then again, I was a math major. So, but basically, there's a couple of different concepts we want to get you to understand. Is one, you can have a single server queue, and that would be similar to you going to a hot dog cart. One guy there, you're in line, you can't have anybody else serve you. All right, I got interrupted a little bit there, sorry. But queuing theory is an applied theory of mathematics. Two different ones, like I said, the single servers, like you and hot dog cart, one server, only one line. He can only serve one customer at a time. A multi-server is where I'm going to provide services to many customers at the same time, but basically one queue. So that'd be similar to a bank, where you get set in that long line, and then you've got, 3 or 4 different bank tellers. So they're still come in, go out one end, come in the other, but I have multiple people serving me at one time. A grocery store, you think, well, gee, they've got, really what have they got? They've got multiple single server lines. I don't think I've been to a grocery store that would have a multi-server queue that I can think of. Target may get the closest, but I think once you get to a certain point, you don't have a choice to branch off. But once you get in line, you're stuck with a single. So it may be a mini multi-server branching to a single server when it actually comes together. Now, a couple of the key factors with this queuing theory is how fast are customers arriving, what's its arrival rate, and then how long does it take to actually serve that customer. So what's the average time spent, fulfilling that request. Now, what queuing theory tries to do mathematically, it tries to predict the queue time. How long am I going to be in the queue? What's the average size of the queue? What's the maximum size of the queue? And you can kind of think as you're going through this, like, well, gee, if I had a print server, I'd want to know, how long are print jobs sitting in there? How much memory do I have to allocate for a queue? If I know the average size or the average size of the print jobs, I can kind of maybe engineer that correct size, based on what comes in. So that's what queuing theory tries to do. So it just tries to predict queue time, how long are you in a queue, how long, what's the average, and what size of the queue do you really need that you should engineer to. And here's just a graphic of some of this stuff where you got the length of line, how long are people in the queue, how long is their service time, how long does it take the server to provide time, and then from a customer standpoint, what is the response time from the time you walked in to the time you leave? Because isn't that when you go to the bank, it isn't so much how fast is it in front of the teller. It's from the time you first stepped in line to the time you left the server is what you worry about. You want to know what that full response time is. And that's kind of what queuing theory is trying to do, trying to engineer that to come up with the best way to maximize service. Now, a couple of applications that we use, one is, at least as far as computer science is concerned, is categorizing data. How do I rearrange data without really destroying the sequence with it, when it comes in? Or two, the second one would be a queue simulation. How do I study the performance of that bank? How their queue is working? Decide whether they need to add another teller or not. So let's look at the first one. We're looking at the categorizing data. So what have I got? I'm basically going to say I'm going to create 4 queues. And in this case, I've got, 0 to 9, 10 to 19, blah, blah, blah. And then basically what I'm going to do is I'm filling these queues. What am I going to do? I'm going to make a choice as far as the number that comes in, which queue does it go to based on the number that it was being accessed. And then, of course, how do I print the number. So you can kind of conceptually see where this is going in. So how do I fill it? While I keep getting data, I'm going to read the number. If it's less than 10, goes in one queue, 20 less. So conceptually, this one's not that difficult to populate the queues. Now, here's your, before you called all the field queues, what'd you have? I had a heap, which stores all the data, and all my blank null head queues, and then all my pointers pointed to the start of my queues. And then as items came in, they're going to get placed into, the various queues based on the number that's being, entered. So it just, basically, I think that algorithm, it's going to just read the number and decide which queue does it go into and go through. The second one would be a simulation, a queue simulator. And basically, what do I got to do? I got to create a queue. So you're going to do that once, and you're probably going to print the stats once. But new service, do I have a server free? So is there somebody, if you're going to the movies, somebody's always saying, okay, next in line. Maybe you get that with the bank too, I guess, basically the larger bank. Somebody's got to indicate to you that somebody's free. So new arrival, how fast do I get servers free? Is my service complete? So you're going to simulate, go through each one of these, simulations. So here we're going to kind of go through a taffy simulation. So how do I queue, for people buying saltwater taffy? So you're on Mackinac Island buying saltwater taffy. So here you're going to create your queue. You can do that one time. And now I'm just going to loop through, either I'm totally out of time or there's no more customers. Then I'll be done. If there's a new customer, what am I going to do? I'm going to call the new customer routine. I'm going to pretty much say what I'm going to do. I'm going to say, give me the address of the queue, start the clock, and, give me whatever customer information. The server free, going to do the same thing. Give me the pointer. You're going to keep track of the clock, understand what customer status is. Are they in or out? Are they busy? Are there any more customers? And the service complete basically says what? I mean, I've still got the queue. I've got my clock. So it's basically running through when have I finished everything. If the queue's not empty, tell me there's still more customers, increment the clock, go back through. When I'm totally through processing all the customers, now go ahead and print the simulation. So what's a new customer do? New customer basically says, hey, I get randomly, customer's going to show up. So if it's a new customer, I'm going to increment, give them pretty much like pulling a number at the deli. You're going to give them a number. You're going to store his data, take that number, store it in the customer data. You're going to store the arrival time in his data because I want to know how long this customer's been in the queue, and then I want to add that data to the queue. So that's all new customers is doing. Now the server free is going to determine if a server's idle, not busy. So if the clock is greater than the start time, so that means, okay, it's just basically I'm trying to determine if the server's idle. If the server's not idle, you want to check if there's anybody standing in line. Or I should say is idle, so the server's idle. Check if there's anybody in the queue. If there is people in the queue, take one off. Then update the status of the customer number, arrival, start, finish date, time, and then set more customers to true and go on through. So you're just making sure that you do this. And then when everything's done, basically what you're going to do is you're going to pretty much print. You're just going to make sure all the data is gathered in this case, set the wait time to start, to status start. You can set it to start minus arrival time, increment the number of customers. So not too big of a deal, and go through that. Now, and then here's your average print. So you can tell that stacks and queues are related. Similar functions, similar processing, just where do I add items and where do I get items, or how do I put things in and take things out? Those are the two biggest aspects. Stack, I'm pushing them on, popping them off. And then a queue, it's first in, first out. Come in at one end, leave on the other, and then put the tools together to handle the processing of data based on reports or anything else you want to do. So hopefully this helps. And if it doesn't, let me know. Talk to you later. Bye-bye.